Hello, my name is Robin Rader. I'm doing a presentation on building static pressure. This talk is about achieving accurate measurement, control, and the impacts of that control in cold climates. So that's who I am. So with building static pressure, there is an error that is induced into the sensing array during cold weather when there's a height difference between the indoor air reference and the outdoor reference. In this case, the induced error is driven by temperature difference similar to the pressure difference within a building due to stack effect, with the error causing the reading to read high. Depending on the height and temperature difference, the error can be as significant as 4 times the control point. So why does building static pressure matter in the first place? So negative pressure within a building causes drafts in all the wrong places. Clients, receptionists, security guards are subject to harsh temperature swings. So at 1/10 of an inch of static pressure, we're at the upper boundary that an automatic door closer can function. At 0.2 inches of static pressure, manual operation of a standard 3/0 door is physically difficult. You've got to pull it shut with 2 hands or put your shoulder into the door to make it work. So the 0.05 inch set point that is the industry standard is a good positive building static set point. Automatic doors should be able to function acceptably at this pressure. These days, commissioning agents are often setting 0.03 inches as the building static pressure control point, as the accuracy of our controllers increases. Just for reference, 1/100th of an inch is the minimum control point allowed for sterile room boundaries like sterilization or compounding labs and things of that nature. So significant static pressure variation is imposed on a structure simply by keeping it warm, and that's called building stack effect. So from ASHRAE Fundamentals, which describes this effect, for a building with a roof height of 75 feet and indoor temperature of 70 degrees F and an outdoor temperature of minus 40 degrees F, the internal static pressure varies 3/10 of an inch between the ground floor and the underside of the roof, with roof elevation at a positive 0.15 inches and the ground floor at a negative 0.15 inches. This relationship can be shifted by drawing in excess incoming outside air compared to the exhaust, relief, or exfiltration air. The necessary amount of excess outside air depends on the tightness of the building. So to achieve this 0.05 positive pressure at grade in this example, the pressure at the roof level would have to be increased to 0.35 inches of water column. Turns out that that's nearly impossible to do. So you end up running buildings at a negative pressure at the ground floor on these taller buildings. The relationship between building static pressure and infiltration or exfiltration is similar to Ohm's law, where voltage equals current times resistance. If we're looking at this on the stack effect issue or correlation, in this case, voltage is caused by the warm building surrounded by cold outside air resistance, or maybe we'd call that the potential. The resistance is the tightness of the envelope, and the current is the amount of unwanted infiltration or exfiltration. The tighter the building, or the better they are, the less unwanted infiltration or exfiltration. Note that V increases with building height for a given temperature difference between the inside and outside. So again, just to keep the building warm, you have this stack effect going on. In Alaska, the author's home state, there are no high-rise buildings north of Anchorage based on the building code designation. So highest building in Fairbanks is 75 or 80 feet along those lines. Cities like Calgary, Edmonton, Chicago, and Minneapolis contain buildings with the greatest stack effect potential because those buildings in those cities get quite high. However, in Fairbanks, where I live, there are extended periods of cold weather. So while we don't have the greatest stack effect, we do have a significant stack effect, and it occurs for a long time. Far too long to allow the issues with stack effect to go unaddressed. Maintaining positive building pressure on the ground floor of tall buildings in cold climates is impossible. The interior must be designed to account for significant infiltration. So what do we do? So here is the building that our company became first aware of problems with sensing stack pressure. This building is 75 feet high. It's got a large two-story entryway that you can see there. Everybody enters through those double doors. At the entryway, there is a security guard just outside the entry who, if there is a significant infiltration, is subject to that infiltration. So at a minus 50-degree day, that security guard is in trouble if we have significant negative pressure. So we're going to talk about entryways a little bit. The typical Arctic entry has two sets of doors. The distance between those doors should be about 15 feet so that one set of doors has time to close before the person walking through this entry gets to the other doors. And that doesn't happen all the time. You can have multiple people accessing it, but in general, you just have one set of doors open at once. And so a good design criteria for doors, for well-traveled entrance doors, is 3 CFM per linear feet of crack length of the door. And so that times your design temperature will give you your BTUs that are necessary to heat this entry. Now, it's that amount of BTUs is significantly higher than your conduction and infiltration, or your typical infiltration through this entry. And so what you do is that you take that calculated value and you assign 1/3 of it to the cabinet unit heater in the entry, and on the other side of that entry you put 2/3 of that value. Now, the best heaters for typical entryways are cabinet unit heaters that are configured to pull air off the floor, to heat it up, and to blow it out the top of the cabinet unit heater. These cabinet unit heaters should be sized so that they have a high flow. So maybe a single row coil with a large air handling or a large cabinet unit heater that cycles significant air. So what you're doing is you're essentially vacuuming the cold air off the floor and you're pushing it up, say it's 85-degree air. That air is going to rise to the top, but the fact that you're vacuuming significant air off the floor causes the warm air to be pulled down to the floor. So here's an example of that cabinet unit heater, pulling air off the floor low and blowing it up into the air. So here's a ceiling mounted cabinet unit heaters, and these things don't work very well. They don't give you a comfortable entry. They well keep the sprinkler head from freezing. But for instance, if you had automatic door, they would not keep that automatic door from freezing. And you'd have continuous issues with your automatic door during cold weather. Now, one thing to note though is if you don't have glycol, if you're just running water in your hydronic system, then this type of cabinet unit heater is the only one you can use. If you used the previous cabinet unit heater pulling air, cold air off the floor, you freeze the coil. So that's one reason why we're showing this type of cabinet unit heater. So this picture pictures an air curtain, and air curtains are becoming popular. They are cited in ASHRAE as a way not to have double doors, but for very cold climates like Fairbanks, they need to be avoided because the velocity does not keep the airstream at the door, but when the door opens, the differential pressure is high enough to pull that stream off of the door and to allow cold air to go around it. So the last thing you want to do is put in an air curtain and skip the two sets of doors. And in fact, this cabinet unit heater does very little good. What happens is the cold air gets pulled off of the door, or the hot air gets pulled off of the door. It immediately goes high and is no good to the occupants around this entrance. So we're getting near the end of the talk on double doors. So this is a picture of a split entry on the one side. We've done this in hospitals, for instance, where you have quite a bit of traffic. You can split the entry so that you have less possibility of multiple people going through the entry and keeping both doors open at once. And so then the last picture here is a set of revolving doors. And I just wanted to show this. And you see these, and they seem to work. I've seen them in Calgary, and they seem to work. But I will say that there are no revolving door examples used in Fairbanks. In a few places where they have been used, they've been pulled out. And I'm not sure personally why that is. I'm guessing that they simply can't keep them working in cold weather, that they tend to ice up. But anyway, that's our experience with revolving doors. Okay, so building entry design recap. Vestibules with 2 sets of doors and reasonable travel distance is the foundation. Split vestibule separating incoming and outgoing travel flows to further decrease potential of both sets of doors to be open simultaneously. And again, this has been done in a hospital, but other than that, probably is not necessary. Radiant heating to prevent automatic doors from freezing at the floor due to ice buildup. So if it's new construction, radiant floor is a good idea in an entry that has an automatic door. It's the best way to make sure that the track of that automatic door stays warm enough that there's no freezing. Weight heating capacity towards the occupied side. Assume cold air escapes the vestibule. So don't think that a lot of heat in your vestibule is the way to go. It's much better to heat outside the vestibule. Try to pick that cold air up that's flowing along the floor. Wall-mounted cabinet unit heaters are the best way to go. Got to protect the coil with glycol in this case. For high stratification lobbies, that is lobbies with high ceilings, drawing air into the heater as low as possible, select a unit heater with high flow, low delta T configuration. Under cold conditions at minus 20 F, switch control modes to run the cabinet unit heater fan continuously, modulating the coil flow to maintain temperature set point. So here's a good point. Cabinet unit heaters are often just run off of a single line voltage thermostat, and this is a perfectly fine way to do it. However, an improvement on that is to put a valve, a modulating valve on your coil, and interlock the control signal through a relay, and then start that fan and allow it to run continuously at minus 20, and then just modulate the coil to maintain temperature. And that continually cycles that air is what that's doing. Work with an architect to provide wing walls to protect lobby seating areas or receptionists from cold air racing along the floor. So just picture in cold climates, there's nothing you can do when the door opens. There's cold air that comes rushing into the building. Your heaters need to be configured to grab that air and turn it into warm air as soon as possible, but that takes some time, and there needs to be some distance for that. And so receptionists, the entry to a receptionist area should be as far away from the door as possible. If you have lobby seating right off that entry, it's best to have a little wing wall, like a 2 or 3 foot high wing wall that causes the cold air to have to run around that wing wall before it gets to the people seated. So pressurize entry area closing off return air openings. This also requires closed doors at the entry boundary. So we did this at the Rabinowitz Courthouse. That was that picture of the building that I showed. This was necessary because the security guard was in the airstream for an 8-hour shift. And so these poor guys are subject to 40 and 50 below air rushing into this building. And so what we had to do, we had in initial construction, we had everything that we thought we could do. We had radiant heating below these security guards. We had cabinet unit heaters. We had a good entry, and yet they were still freezing. And so we did one more modification because we had doors all around this 2-story entry. We were able to close all those doors, and we were able to close off the return air openings out of this building and pressurize, or out of this vestibule, and pressurize the vestibule. And so that was the last thing we did, and it helped quite a bit. Okay, so now we're going to talk about sensing. So accurate building static pressure sensing is the foundation for good control. Accuracy is subject to both wind and temperature difference. And so we're going to talk a little bit about trying to attenuate wind effects. So this picture is a picture of a stratification area around a building. And so the wind is blowing from the right-hand side of this picture onto the wall. And so the outdoor reference is in that stratification area. And the stratification of wind on a building is much higher than your static control point. And a 15-mile-an-hour wind, for instance, can move, I'm not sure, but it's like 0.15 or something like that. It's pretty significant compared to your control point. So you have to somehow handle that wind pressure. So one way to handle wind pressure is an outside reference with a wind attenuating head. And you can see that at the top of this building. Essentially, it's two plates with a little opening in the center of the bottom plate. And so what that does is it causes the wind being blown through that head to be orthogonal or 90 degrees to the sensing point. And so the wind has no effect on that sensing point in that case. Now I drew the picture of it above the stagnation range. You know, exactly where that is on a building is kind of difficult to determine. Certainly you'd like to have the thing as high as possible. You want to mount it to the highest thing possible. And then I also put a picture of this, of an outdoor reference on the other side of the building. And so this is on the low pressure side. You could use this to average. So you could pipe these two sensors together so that when the wind blows against one, it's negative on the other. One thing to note, though, is it's not really a match. The negative pressure on this side does not match the positive pressure on that side. So this is not necessarily the most accurate way to handle this. And I'd say in areas of high wind, this is probably a two-sensor situation is probably not adequate. So anyway, this is another picture of a way to do a two-sensor array on a building and average that input. So those two sensors are mounted at the same height as the indoor reference. And so at that point, if that's the case, then you don't have off calibration of your sensing array during cold weather. Buoyancy effects. So you can, we're going to talk about buoyancy effects within the sensor array. So this is the buoyancy equation. You can find this equation in ASHRAE. It's the equation that determines stack effect. So stack effect is happening within your sensor array if your outside sensor is at a different elevation than your indoor sensor. Okay, so meteorologists also figure out pressure changes within the atmosphere, in the low atmosphere. And I just wanted to reference this hypsometric equation just because. And airplanes also have to keep track of static pressure. So an airplane taking off in warm weather will have to correct their altimeter if they're flying into an area of cold weather. So, for instance, this table shows that if you're flying from warm weather into an area of 40 below, then there's a 240-foot altitude correction that has to be made for every 1,000 feet. Comparisons of equations. So these equations don't necessarily render the same result. And so I went through these calculations and found that this was the result of these three equations. So the buoyancy equation is the equation that I have decided to use for building static pressure correction. And so here is a graph of the calibration error. So we can see it and I personally don't think in metric. I just put this down because I wrote an ASHRAE article and they require metric. But at minus 40, you can see that if you look at the right-hand side, which is the pressure differential from the base of the measurement, we have nearly 0.2 of an inch of static pressure difference between the 20-degree or 68-degree temperature and the minus 40-degree temperature. So what that means is if you calibrated your sensor at 70 degrees and set the zero at 70 degrees, then at 40 degrees, this thing is going to read higher by almost 0.2 of an inch. So it's very significant. And so this is just a little bit different chart, which is a error based on, let's see, what have I got here? Based on 40 degrees temperature change, and then I just changed the elevation. So you can just see if you've got a 100-foot building, even a 40-degree temperature change is significant. So how do we reduce errors due to temperature? So on the left there is a typical pressure gauge. It's in the range of building static pressure with 0.05 inches being the typical set point. On the right there is a typical building static pressure transducer. So you can buy a auto zero transducer, and this transducer, for instance, could be set to reset the 0 point on every night. So what are the pros of doing that? One, it's inexpensive. This sensor isn't significantly more than other sensors. And it would work well with wind attenuating reference point configuration. So when you configure your, or in the case of a commissioning agent, if the designer configured the building static pressure sensing so that there was a wind attenuating head high on the building, then this auto zero transducer could work pretty well with that. But what are the cons of doing it? Well, it's not going to agree with a passive manometer. So anytime you put a passive manometer to look at the pressure, just a gauge, your transducer is not going to agree because you don't auto zero your manometer every day. It also has to be zeroed on a daily basis with the equipment off. So on buildings that you never turn the ventilation system off on, say a hospital for instance, running 24 hours a day, then you have no point where you can zero it. And it doesn't agree with the actual condition, but only reflects the pressure above the quiescent state, or meaning it only reflects the pressure at the time of the zero, that the zero was set. So if you have a significant temperature difference that occurs between those two times, then you'd run into trouble. So anyway, I don't like the idea of an auto zero transducer. We've never used them in our designs. So we've done, since we've become aware of this issue, done various things. One thing we've done is we've used two transducers with two manometers. One set of transducers is essentially across the entry. We've got the outside air sensor at 7 feet above finished floor at the entry, and the interior sensor may not be near that entry, but it's at the same elevation. So this transducer is not affected by temperature. However, because the element is low at 7 feet, it is subject to wind stratification. The other pair incorporates a wind attenuating head at the top of the building. And it's got some length difference between the outdoor reference at the building entry and that wind attenuating head. So we run a calculation that offsets this sensing based on temperature. So the DDC system knows what outside air temperature it is, and it calculates a correction factor based on that temperature. So this is what we've stuffed into the DDC system to calibrate that error. And again, I'm a English unit person. I'm 62 years old, so those are the units I grew up on, and so that's what I'm showing here. The metric system is maybe slightly easier because it doesn't have a gravitational acceleration in the system, but anyway, that's what I use. And you also need to use absolute zero temperature scale. In this case, it's Rankine. So that is the equation. So this is just my opinion on how transducers ought to be located. Most control installers like to locate the transducers remotely near one of the reference points. However, I think that's a lousy idea because they're easy to get lost. They're not near the DDC controller, and so if you have to calibrate the transducer, it's hard to calibrate it. So I make it a point to specify it differently. I call for the transducer to be located in the mechanical room within a panel right next to a passive gauge. Now, differential pressure transducers are often sold with a display of the pressure. Personally, don't like that. I like to have a gauge where it's a separate gauge that I can use to calibrate the transducer. So anyway, that's what we specify. So there is often a long length of tubing in this case, and I think that's fine personally. It averages out wind effect pressures, door effect pressures, and I haven't found any problem with having long lead lengths from the pressure sensors to the transducers. Now, I will mention that a high duct pressure sensor is different. That needs to be sensed quickly. However, that typically happens within the mechanical room upstream of the fire smoke dampers that are at the mechanical room boundary, or often at the mechanical room boundary. So that's a little bit different case. So commissioning of this static pressure reference system. So a static pressure reference is a good candidate for commissioning because the problems with the reference aren't readily apparent. A broken or disconnected reference tubing can appear to report varying pressure information similar to what might be expected. And we had this in one of our buildings. We spent several months arguing between myself and the client rep about what the problem was with this building static pressure in a building, and lo and behold, they had not piped the building static pressure all the way out to the exterior of the building. Static pressure references should be checked. They're pretty easy to check. So the way I would check building static pressure is I would plug the outlets and simply impose a pressure onto the tubing system and pump it up to, say, 10 psi using the typical thermometer, which is used by pneumatic controls technicians. But you could use anything to pump this thing up. So you pump it up, make sure that there's no holes in your tubing, and that because you saw these plugs being installed, you know where the ends of the pressure is being sensed, and then you just make sure that the pressure is held at that 10 psi for some length of time, probably just a few minutes, because there's essentially no volume in this tubing. So that's a picture of the thermometer. Okay, so we're at the end of the talk. So why isn't the sky falling? For many, if not most buildings, accurate knowledge of building static pressure under cold conditions is not required for adequate building operation. How about that? So typical operation of many buildings during cold weather operation has the outside air damper set to minimum and the relief air damper set full closed at some outside air temperature set point determined by the building operator's experience or the sequence of operation possibly. But typically it's something found by the, it's got to be found during cold weather. Once this is done, nothing more can be done. In this case, true knowledge of actual static pressure is academic. So here we are, we've talked about this thing for this last hour, and for many buildings, it's really not that important. However, as the building becomes larger or is more sophisticated, accurate knowledge of building pressure becomes more important. It is of great importance if additional outside air is added to maintain building static pressure. This might be true for hospitals or somewhat exotic facilities. Accurate understanding of these issues may prevent the commissioning agent from getting caught during commissioning with unexplainable results. So really, that's the value of this talk is for commissioning agents, is that we need to know what is happening and help the designer to recognize that we may or may not need accurate knowledge of building pressure during cold conditions. And that concludes my talk. I appreciate everyone watching. Thank you.